So my project is better known as Nemo's Little Secret, but it's also known as Determination of Estrogen as a Trigger of Protandric Colony Formation of Amphiprion ocellaris. Now, I don't know how many people know this, or how many people have watched the movie, but there's a little secret that they don't tell you in the movie of Finding Nemo. Clownfish change sex. Now, that isn't even really that weird in the world of in the world of fish. In marine biology, tons of fish change sex. What makes these guys really unique is that they practice protandric sex change, or the sex change from male to female. In the rest of the animal kingdom, everybody changes from female to male. So like a harem of lions, where there's the one king male and then there's the group of females that he rules over, this is exactly the opposite. There's a queen bee fish that rules over all the other males and keeps them in line. Now, what's really interesting about these guys is that the other fact is that they form colonies. And there is always one female, one mature male, and the rest of them are all immature males in the colony. Doesn't matter if there's 2 fish or if there's 20 fish. There's going to be either one female, one mature male, and the rest are all immature males. Now what happens is that if the female is removed from the colony, whether she gets eaten by a barracuda or she gets sold at the pet store because she's the biggest and the most pretty, then the mature male changes sex to become female, and one of the immature males, the next one in line in the dominance hierarchy, changes to become the mature male and becomes a new breeding pair, like in a pack of wolves. Now, what I'm trying to figure out is how the female prevents the sex change of the male fish. Because as long as she's there, nobody changes sex. As soon as she's removed, sex change occurs. And then as soon as the new female is there, nobody else changes sex. Therefore, it's assumed that it has to be the female controlling the sex change in the colony. Now, what we know as marine biologists is how the fish change sex. We know why they change sex, and we know when they change sex, but we don't know how they know when to change sex. That's what I found out this year. So what I actually did is I set up a colony of clownfish that were all immature males, and these were 12 fish. And I then watched and observed as a full completion colony came into existence in my fish tank, which is the female and the mature male, and the rest is immature males. Now during this time period, I took water samples every day during class. After I had the full colony, I actually used high-performance liquid chromatography, otherwise known as HPLC, to test the samples and look for estradiol, which is the main sex hormone of fish. Now, chromatography, for those of you that don't know, sounds like it's going to be something really big and complicated, but it's actually really cool to learn about. What happens is I inject my water sample into the machine, and then these 2 different solvents flow through the machine. In my case, it was acetonitrile and ultra-pure water. Now what happens is as the gradient or the test runs, the different ratios between the 2 solvents change. Now, the different substances that are in your sample that you injected into the machine have stuck to your column. And what happens is as the ratios of the 2 solvents change and flow through the column, different substances that are stuck to the column from the sample flow off at different times. Now, because the ratio changes at the same time during each one of the tests, you're able to isolate different materials that come off the column because they'll come off at the same time during each one of the tests. Now that's what I did, and I was trying to isolate I was trying to isolate estradiol, and I also ran a positive control of the estradiol to find out where in the sample it was actually coming off, because in these samples of the water from the fish tank, it is a habitat, so there are lots of other different substances that are in there. I don't want to be getting a reading of salt or a reading of the waste products from the fish or dissolving food. I just want to see the estradiol. Now here are my chromatographs for 200 nanometers and 280 nanometers. And as you can see, there are peaks that line up throughout the area, and that's where something of the same substances come off of the same time. Now, what I did was I isolated peaks where I saw estradiol coming off of, and there were other peaks that were underneath it from just my regular water samples. So, there are 2 samples there that I isolated off of my peaks. Now, what I did to find whether there's a statistically significant difference in these water samples was I used a chi-squared test. Now, what I first did was to find the amount of estrogen or estradiol that's already in the sample, is you take the area under the graph, and that gives you the amount of whatever substance you found under that peak. So then I ran a chi-squared test where there was the the expected, which was my negative control, which was just a fish tank that had no water or no fish in it, regular setup tank, because I needed to see there is a regular natural level of estrogen in any sample of water, and I didn't want to be reading that as something that the fish were giving off. And then I compared that to the observed values, which were what I had seen off of my fish tank. Now, what you do is you take the observed values minus the expected values squared, divided by expected, and that gives you your chi-squared value, otherwise known as your critical value. Now, what happens is if the observed is equal to the expected, then the hypothesis cannot be rejected. If the observed is not equal to the expected, then your hypothesis can be rejected and you found something that's statistically significant. Now, what it means by the critical value is that if my chi-squared value is above that critical value, there is a statistically significant difference between my negative control or the expected value and my samples or the observed values. So what I was able to find is that at 200 nanometers I was able to find a peak where the expected value was much more than the observed value, and the value was over the critical value of 3.84. Now, there was no difference in the area for the 280 graph nanometer. Therefore, the null hypothesis can be rejected, and there is a statistically significant difference, meaning that it supports the hypothesis that there is, the female is releasing estrogen into the water to prevent the sex change of the males. Any questions?